And we're off. We start off with a review of our friend SOHCAHTOA. By this time you had better be quite familiar with SOHCAHTOA. In a triangle, a right triangle, the sine of theta, whatever theta may be, the sine is equal to opposite over hypotenuse. Hey, let's go ahead and fill in numbers here. You should know well that if you have a right triangle with a hypotenuse of 5 and one leg of 3, the other leg must be 4. So that 3 squared, 9, plus 4 squared, 16, will equal 5 squared, 25. So in this case, sine of theta means opposite over hypotenuse. That would be from theta's perspective right there, opposite over hypotenuse, 4/5. And I have these lined up this way because remember that sine is the reciprocal of cosecant. So cosecant must be 5/4. Cosine. Cosine is adjacent over hypotenuse. So we have from theta's perspective, adjacent over hypotenuse. That's 3/5, 3/5. And cosine's reciprocal, secant, is therefore 5/3. Then tangent of theta. Tangent is opposite over adjacent. Those are not threes, those are squiggles. Opposite over adjacent. So we have opposite over adjacent, that's 4/3, that's 4/3, and the reciprocal of tangent, which is cotangent, will be 3/4, and we've got them all. As long as we know all three sides, or even just two sides, we can figure out all of the functions. Now, moving on. We have on page 497 the rain gutter problem. The rain gutter problem says we have this sheet of metal, probably aluminum. It's 12 inches wide. It's very long, it's going to be a gutter, but it's 12 inches wide. We're going to bend it right there and right there and make it into a gutter. The question is, at exactly what angle here do we bend it at to get the maximum possible area inside this gutter, given that we have 12 inches and we're going to bend it at 4 and 4. What's the correct angle to get maximum area inside here? So here's the idea. We're going to bend those two sides up, bend them up again and again and again, and we want to bend it up until we get to the point where this area has been maximized. You say, oh, well, it's obviously going to be straight up because then it's the tallest. Well, not necessarily so. Because yes, as I move them straight up like this, it gets taller, but it gets narrower. If I go down like this, it gets wider, but it gets shallower. So where in the world is the point where we have the greatest possible area? Someplace in between. A little common sense might say, oh, well, it should be 45 degrees, halfway between flat and straight up. No, it's not going to be 45 degrees. Let's find out what it is. First, we need to come up with a calculation for this area. To find this area, we're going to break it into two triangles, there and there, plus a rectangle. Problem, of course, we know what this length is, 4. We know that's 4. We know that's 4. Therefore, this is also 4. What we don't know is this height, because that height changes depending on the angle theta that we use. So let's figure out what is the area. All right. First, we established that we're going to measure the angle from the horizontal up this way. That's going to be our theta right there. A little bit of geometry tells you that if this base is going to be parallel to the top, and we have here a transversal, if this is theta, guess what this angle has to be? We have a name for these, remember? The famous Z. This is alternate interior angles, better known as alternate interior angles. If that's theta, then this is also theta. So we really don't need this. We know this is our theta. Alright, so what? Let's figure out the cosine of theta. We're looking just at this triangle. Cosine of theta. Cosine being adjacent over hypotenuse. So the cosine of theta, there's theta, we're ignoring this one. Cosine of theta is adjacent over hypotenuse. That's a over 4. A over 4. So if the cosine of theta is a over 4, then what's a? Well, multiply by 4. So a must be 4 times cosine of theta. We just multiplied by 4 and multiplied by 4. So a is 4 cosine theta. Now what's the sine of theta? Why do we care? Well, because we're not only interested in this distance, we're also interested in b as well. So we're going to use sine to find that one. Sine of theta is opposite over hypotenuse, or b over 4. Sine is b over 4. Therefore, what's b? B is going to be, multiplied by 4, b is going to be 4 sine of theta. So we now know what a is. A is 4 cosine of whatever theta is going to be. And b is 4 sine of whatever theta is going to be. Next screen. Alright, so, that's simply filling in the gaps here. Okay, moving on to the next screen then. So now, what's the area of this triangle? Well, the area of any triangle is going to be 1/2 a times b, right? 1/2 times the base times the height. So what is a? Well, we already established that a is 4 cosine theta. I've got these backwards, it doesn't matter, but because multiplication is commutative. But a, 4 cosine theta, I've inserted right here. And then b is 4 sine theta, I've inserted that right here. We now multiply this out. We have 1/2 times 4 is 8 sine theta cosine theta. We have a formula, ta-da! We have a formula for the area of this triangle, which is a function of the angle I choose, theta. Pretty cool. Of course, we don't have just one such triangle, we have 2 such triangles. And therefore, the area of the 2 triangles together will not be 8 sine theta cosine theta, but 16 sine theta cosine theta. So, yes, there it is. 4 sine theta cosine theta plus another 4. No, I'm sorry, that was 8. 8 sine theta cosine theta plus another 8 sine theta cosine theta for a total of 16 sine theta cosine theta. Now, what about the area of the rectangle? Well, the rectangle's width is obviously 4, but what's its height? Oh, 4 sine theta. So the rectangle is simply 4 times 4 sine theta. 4 times 4 sine theta. So that's going to be 16 sine theta. So let's move on. We have, therefore, 16 sine theta cosine theta. That's the area of the 2 triangles combined. We have 4 times 4 sine of theta. That's the area of the rectangle. Now, let's do something clever here. Let's multiply this out. 16 sine theta. 16 sine theta. And now we see we have a 16 sine theta in both sides of this expression. Let's factor it out. Factoring out 16 sine theta, here we're left with cosine theta plus, the whole thing comes out, plus 1. Now we have, congratulations, we now have a formula for the area of the whole thing given simply the angle theta through which I bend that piece of metal on, of course, both sides. So, let's go to Desmos. We've got our formula. 16 sine theta times cosine theta plus 1. We go to Desmos. Oops, I don't have it there. One moment. Okay, there's Desmos. And I've already put the formula in here, 16 times sine theta, or sine of x, times, in parentheses, that's important, times cosine of theta, or cosine of x, plus 1. Let's see what it looks like. When I first saw this, it kind of scared me, because I'm looking at that going, whoa! I'm supposed to use this graph to find out where the maximum value is. I'm trying to find where is this at its maximum. I want to get this is the formula for area, right? I want to find where is the area the greatest. Where is it the highest? I look at this and I say, whoa, that's really bizarre looking stuff. It looks to me like it goes up infinitely. Is there no maximum area? If the graph says there's no maximum area, that would imply there's something wrong with my formula, because there's no way I'm going to bend that thing and have infinite area. That's silly. So either we messed up on our formula, or, haha, watch this. We have to back out a bit, and we say, oh, it does have maximum values. But why so many of these things? Well, this is assuming that theta can go infinitely to the right and infinitely to the left. But we're only interested in values of theta between 0 and 90. We only need from 0 to 90. We only need from 0 to pi over 2. Where is that? From 0 to pi over 2, let's see, let's zoom in a little bit here. From 0 to pi over 2, wait, not pi over 2, from 0 through, okay, this graph is actually going to take us all the way to 1 pi, 0 to 1 pi. I guess the thinking is, yeah, you could bend it past 90 degrees all the way in like this. I think the graph will make more sense if we recognize that we're going to look at the area for theta equaling 0 past 90 all the way to 180. So that would be from 0 to pi. So we're looking at values from, we're looking at values from here to here only, from 0 to pi. So, with that in mind, let's zoom back out. I could change my vertical scale. Hey, you know something that would be easier? Let's change the vertical scale so that we can see this more easily. This goes as high as about 21. So let's change our vertical scale. The y-axis, let's have it not go all the way there. Let's have it go from -1. We'll have the vertical go from -1 up to, and how far does that went? Okay, let's go up to about 25. Up to, oh, that's the x-axis. Wrong. Oh, okay, well, let's change the x-axis a little bit also. Let's go to, I don't know, 2 pi. 2 pi. All right, back to my y-axis. From -1 to, let's send it up to 22 should do it. And now we can see things more easily. Okay, so here we have it going from, over here, from 0 to pi. Our maximum value is right here. Where is that maximum value? We touch it, we see that maximum value is at pi over 3. The angle of pi over 3 gives maximum volume, maximum area of about 20.8 square units, square inches. So pi over 3, what is pi over 3? Pi over 3 is 60 degrees. We have solved our problem. Notice if we go past 60 degrees, the volume begins to drop off dramatically until we get all the way down here to a point at pi where I should say not volume but area, we get all the way to 1 pi where the area is 0. So we start off with an area of 0 when it's flat. The area begins to increase. It increases rapidly. And when we hit 60 degrees, we're at maximum. And then we keep on going to 90, where we might have guessed it would be the right place, but it's not. And we keep on going until we get all the way down to 0 again. We have a maximum area at 60 degrees. Notice at 90 degrees, we were right here. At 90 degrees, we had an area of only about 16 according to Desmos. 16 point something right there at 90 degrees. All right, moving on. I kind of like that problem. That's a cool problem. Let's go on now to this. Very important to recognize. We talked about this at the tail end of chapter 6. The relationship between A and B. We know that A and B have to be what? Give me that C word. Congruent. No, not congruent. A and B have to be complementary. They have to add up to 90. Okay. What's the sign of B? The sign of B is going to be opposite over hypotenuse. Sign of B is B. Oops. Sign of B is B over C. What's the cosine of A? The cosine of A being adjacent over hypotenuse is B over C. Whoa, they're the same. The sine of B and the cosine of A are the same thing. And what's that special relationship between A and B? They're complementary. So as we said in the previous chapter, the sine of an angle will be equal to the cosine of its complement. The sine of an angle will be equal to the cosine of its complement. So, and that's true of all cofunctions. Maybe that's where the concept of cofunctions came from. Cofunctions of complementary angles are equal. So the sine of A will be equal to the cosine of B. In right triangles, we know that A and B are always going to be complementary. So as long as A and B are complementary, the sine of A will equal the cosine of B. The tangent of A will equal the cotangent of B. Co-functions, tangent, cotangent. The tangent of A equal to the cotangent of its complement B. The secant of A equal to the cosecant of B. Secant and cosecant, co-functions. Co-functions. So the secant of A being equal to the cosecant of B, provided that A and B are indeed complementary. So some quick examples here. That means that the secant of 80 must be equal to the cosecant of 10, because 80 and 10 add up to 90. Okay, end of that story. Oh, watch out, because you'll come across this in radians occasionally. For instance, what would be the, let's see, the tangent of, how about pi over 3 will be equal to what? Well, what's the complement of pi over 3? Pi over 3 is 60. The complement of 60 is 30. What's the degree measure for a 30-degree angle? It's pi over 6. So the tangent of pi over 3 will be equal to the cofunction, the cotangent of pi over 6. They are cofunctions. Pi over 3 and pi over 6 adds up to 90 degrees. Therefore, they must be equal. Okay, next. Solving a right triangle. This is all about SOHCAHTOA. This entire section is really just a review of SOHCAHTOA, one could say. Okay, solving a triangle. To solve a right triangle means to find everything they didn't give you. Solving a right triangle means if they've given you this angle and that side, we're supposed to find the other angle and the other two sides. Well, finding the other angle is trivial, right? If that's 40, B has to be 50. They must be complementary. That was simple. A and C require a little bit more work, but this is a review of something we saw back in chapter 6. It's also a review of things you learned back in geometry, whatever year you took that. It's something that I just taught my 10th grade geometry class just a few weeks ago, using SOHCAHTOA to find the values of A and C. So, let's do it. I'm not sure what's on my next screen, but let's just do it right here. Yeah, I created this screen a couple of years ago, so I don't know what's coming next. So, here's my angle that I'm looking at. I ask myself, what am I given? What am I looking for? I'm given the adjacent. I'm looking for the hypotenuse. Adjacent and hypotenuse. Adjacent and hypotenuse, I'm going to use cosine. So I write cosine of 40 equals adjacent over hypotenuse. I look up the cosine of 40. Let's just do a little manipulation here without bothering to change that. If I multiply by c and divide by cosine of 40, I find c equals 2 over cosine of 40. That's a little bit of basic algebra 1 type stuff right there to find out what c is. So then I just put in my calculator 2 divided by the cosine of 40, and bang, I get my value of c. I can also find a the same way, except with a, what am I going to use? To find a from the 40-degree angle's perspective, a is its opposite, and the 2 is the adjacent. Opposite and adjacent, over here, opposite and adjacent, I'm going to use tangent. Let's move on to my next screen here. Oh, also, this is a new example entirely. Okay, so we're done. I didn't get the numbers here. You can do that for yourself if you want to. The book, yeah, this came straight from the book, so you can find what it should end up being in the book. I'm not going to take your time to look it up right now. All right, this one. This is an interesting scenario where we don't know A or B. But we can find out both A and B with a fair degree of ease. But first, let's do C. How do we find C? Well, don't forget your basics. Pythagorean theorem works great when you have two sides and you're looking for the third. Plug them in, solve for C. A squared plus B squared equals C squared. Old friend from long ago, you probably learned that in middle school. 2 squared plus 3 squared equals C squared. 4 plus 9 equals C squared. 13 equals C squared, so C is the square root of 13. Done. C is the square root of 13. So now, what about A and B? Back when you were in my geometry class, if you were in my geometry class, we used this language. There was a page in the geometry book, page 311, that had all the trigonometric values from 0 through 90. And we talked about using the table backwards. Well, you're going to use your calculator backwards. So how do we do this? Oh, and by the way, yes, I filled in here that the square root of 13 is approximately 3.61. Don't use that 3.61 in calculations unless you have to. I've had folks who will then use this one to figure out the value of A or B instead of using the 3 and the 2. This is an approximation. The 3 and the 2 are exact. These were the given numbers. Stick with the 3 and the 2. Don't use that unless you have to. It's only an approximation. Using an approximation to get another approximation makes your approximations get even worse. Stick with the 2 and the 3. So to find A and B, what are we going to do? All right, let's find A first. From A's perspective, that is the opposite side. That is the adjacent. Opposite and adjacent, we have tangent. We will write tangent of my unknown angle A is opposite over adjacent. SOHCAHTOA, T-O-A, opposite over adjacent. 3/2 being 1.5. 1.5. So now, I've got I know the tangent is going to be 1.5, but I don't know what angle gave me that tangent. So we go to the calculator and we use the inverse tangent key. You'll hit your second function key. I believe it's yellow on, at least it's yellow on the TI-83. You'll hit your second function key, and then you'll hit the tangent key, because printed on the background it kind of looks like this. You've got your tangent key, and up here it says tangent to the -1. Well, that's not actually to the -1, that's the way we write inverse tangent. So what do? We put in tangent, we hit second inverse tangent of 1.5, and the calculator will give us an approximation of the angle. I don't know what it happens to be, it's in the book. I don't even know what example this is. Can I find it? 3 and 2, it's here someplace. There it is. And they come up with A being approximately 56.3 degrees. So A turns out to be approximately, what did I say, 56.3 degrees. Then how do you find B? Oh, easy. Just subtract from 90. 90 minus 56.3, and you've got B, because they have to add up to 90. And we've done it. I'm not going to bore you with all the glorious details. Of course, you can always go to the book to find any details I've left out. A cool real-life application here. We've got a river. We want to know how wide that river is without getting our feet wet. So what do? We find a rock over here. We then, let's see, what's the best way to start this? We'll measure, we won't measure anything. We'll simply find a spot down here. And we will then arrange to have a right angle between here and here. We'll make this a right angle. Best way to do that is with a surveyor's transit. A surveyor's transit lets me look through a little tiny telescope and sight on that rock. And then I rotate my telescope through 90 degrees precisely and sight down this way and locate a spot over here that's on that line perpendicular to this line, and I measure this distance, and the book says we're going to measure that distance, and we come up with 200 meters. So it's easy to get this to be a right angle. Then I measure from that corner to here, 200 meters. Then I take my scope and I aim at the rock again, and my transit, my little telescope thingy, will tell me what this angle is. It's pretty cool. And I get an angle of 20 degrees. So I find a spot here, I sight to the rock, I turn through 90 degrees, sight down this way, measure 200 meters, mark the spot, set up my transit right here, aim at the rock, measure this angle, 20 degrees. Well, SOHCAHTOA says that's all I need now. I'm trying to find out how far it is across the river. No problem. From my 20-degree angles point of view, this is the opposite side I'm looking for. Opposite side, I've got the adjacent. Opposite and adjacent, I'm going to use tangent. I write tangent of 20 equals opposite. Let's call it W for width of river. W over adjacent, which is 200. Now I have to simply multiply by 200. I get 200 times the tangent of 20, and I don't know what it is right offhand, but the book tells you. And you have figured out the width of the river without getting your feet wet. I'm going to be doing something similar to this one of these days. We've got some very tall pine trees in our backyard. And those pine trees look like they're tall enough that if they fall, and they sometimes do, if that pine tree in particular near our house falls, it could fall onto our house and crash right through a couple of bedrooms. So the question is that a danger? Do we need to get that tree removed? Is there a possibility that it could reach those bedrooms? But I need to know the height of the tree. To find, so this is not water now in this illustration. To find out the height of the tree, I need to get this distance. I'll measure a distance there. I'll set myself up here. I'll figure out a way to get this angle measurement up to the top of the tree. And if I know this distance from the base of the tree to my position, and I know the angle of 20 degrees, I can figure out the height of the tree and then see if my house is safe or not. Trigonometry in very real life. My wife's been begging me to do that for a long time, and I have not gotten around to it yet. Okay, true confessions. There are additional application problems in the book from pages 500 to 502. They're pretty cool. I suggest that you walk yourself through some of them, because without walking through some more examples, you won't have the practice, the experience you need. So your assignment, page 504, numbers 10 and 18 through 26 even, and then 30, 36, 42, 50, and 54. Very few of these are problems. I think maybe the last two are application type problems. I believe the rest of it is just conceptual, solving triangles and using the property of cofunctions being equal, and that's for complementary angles. And I think that's all that's in there. It's not as bad an assignment as it might look. Okay, that's it. See you later.